Lesson 3, line spectra and the Bohr's model. So in this case here, we're going to be talking about a few different spectral lines. The first one is the continuous spectrum. So we learned about this a little bit when we talked about EMR, and we talked about how light produces a continuous spectrum. And if it was put between a diffraction grating, if you guys remember, we were able to then see this rainbow effect appear above and also a rainbow effect appear below. So it's basically a rainbow above, a rainbow below. And this is produced by either producing a hot matter in a condensed state, whether it's a solid or a liquid, and it's usually heated. So a heated solid is usually what I imagine. So if I draw like a, I don't know, like a brick or something like that, I'm going to say, hey, this brick is on fire. So I'm heating it, and then put that light and focus it through this mirror, this diffraction grating. It'll produce this rainbow effect both above and below. So usually like a filament in a light bulb is a great example of this. So what you'll notice differently in this absorption spectrum, well, it looks just like the continuous spectrum, and I'll make it a little bit more obvious that there is missing some colors. There's almost like an absence of a few different colors, and I know it's kind of hard to see, but it's the same kind of pattern above and below, but it's missing certain colors. So it's a rainbow, except for it's missing. And to do this, we're taking a continuous light. So we're going to have white light. And this could be produced from a liquid or a solid that's heated. And this white light is then put through a cooler gas. So I'm just going to draw this as like a little cloud here. I'm going to say it's a cool gas. Okay, so this cool gas is going to take some of the colors. So the white light, which should be a full rainbow, this cool gas is going to take some of the colors. So now when the light passes through that same diffraction grating, it's going to produce a rainbow except for the colors that were absorbed by the cool gas. So maybe it's taken the red, maybe it's taken a little bit of that green color, a few different blues. It's taking those colors away from this continuous spectrum. So white light consists of Roy G. Biv. And we are taking away the red, canceling it off, taking away the green, taking away the blue. So what's left over is what we're seeing on the farther side. Okay, so for the absorption spectrum, it is white light passed through a cool gas, and it's producing the full rainbow except for the colors that were taken by that gas. Okay, so it says here the cool gas is absorbing certain frequencies of light. The gas then emits those frequencies in all directions, and so the frequency of light that is absorbed appear darker than surrounding continuous spectrum. So black lines. So absorption spectrum, sometimes also known as the dark line spectrum. Oops. Okay, and then the next one is a emission spectrum. Emission spectrum is slightly different, also known as a bright line spectrum. And in this case here is produced by exciting a gas. So we are taking a gas and we're exciting it, either by heat or by current. So the two ways I like to draw this is I'm going to take a heat, apply some fire down below, or if we're talking about a current, it's usually electrically exciting it. So I'm just going to draw a little lightning bolt, and I know it might be hard to see yellow and white. Okay, so this is just a regular gas, sometimes cool, sometimes not. But the gas is either done through a current or heat, or I guess both, and then put through a diffraction gradient. In this case here, what's happening is that heating or the current is making the elements excited and therefore producing these spectral lines. Once again, we'll get into more detail in our next topic when we go into talking about the Bohr's model. But it says here, bright lines of the emission spectrums of a gas are the same wavelength as the dark ones of that same gas. So if I have a bright line in a absorption spectrum and an emission spectrum, in order to tell the same colors, you should be able to quite obviously see that this must correspond with that of the hydrogen, because the wavelength that was being absorbed by that gas is also being emitted by that same gas. And same thing, we kind of go through and we notice that there's a trend between these. Quite often when you look at the stars, you can either see the emission or the absorption spectrums, and it will actually tell you the composition of those stars. So if you see a bunch of black lines and you were able to look at all the different gases and their spectral lines, you can compare them to actually see what it's actually made out of. All right, so there's a few questions for you guys to try on the next